Resistors we saw in the first subsection is the common resistors that we use in a prototype setting. There are a few other resistor types, so some are here, like say the dip, or like it's called dual inline package. So when we talk about breadboard, we'll talk about that. So dual inline package or single inline package resistors are something that is available as well. Likewise, we have some of these sliding resistors, like say variable resistors, like similar to the pot. Say this is the pot, the potentiometer, like which I was talking about. You should have one of these in your kits. So trimmer pots, that is again like you can put them in PCBs and things like that. So these are also available. These are some of the variants that we use. And the most important thing here, so this is we are back into math. We are doing some calculation. We are doing resistance, finding out the resistance of the resistor using color codes. So most of the resistors we use in this module will be color coded. So so these colors in color, or like the bands in these, mean something. So what is that? Like that's what we're going to see. So the resistors in your kit I believe it might be like say 4-band ones. So there might be a 5-band and 6-band as well, but like say I've not seen 6 bands much. But again, like say often I see these 4-band resistors and 5-band resistors. So what does that mean? So here are the the resistance value, how we can calculate. So the colors indicate a number. So you have black, brown, red, orange, yellow, green, blue, purple. Sorry, I believe BB Roy. Okay, so to remember these, like we have. I learned, like say, almost 10 years before, or like say maybe 15 years before, when I was reading about these. Like they taught me BB Roy, Great Britain. So that's blue. Very good. So that's violet. Okay. So then now I think I'm good. So okay. So if you wanted to remember this as well, because we don't. For you, it's like an open book test. And when I was doing my bachelor's, like it was a closed book examination, so we had to remember these. B.B. Roy, Great Britain, very good wife, good son. So that is how I remember these. So this is black, brown, red, orange, yellow, green, blue, violet, and then Great Britain. Then like yeah, we have gray and silver. So this is this is white, I believe. Yeah, good wife, good son. Yeah, so gray and white. Yeah, so that is the color codes you will find in your resistors. So each of those means like a digit. So let's say here yellow is 4, and this is violet, so that violet is 7. And then you have red. So this is the one like which is important, like whether like say it's a 4-band or like a 5-band or a 6-band, depends on the one just before your tolerance. The last one is like always tolerance. So the ones you have will have a tolerance of 10 or 5. So it should either have a silver band or a red band. So always I would start with that. So before like I find out the resistance, my bad, just give me a second. Go back. Sorry about that. So always I'll start with the silver or like say gold band. So that'll be the end, that is the tolerance, and then see how many bands are before that actually. So if you have 3 bands, and this is the one I'll follow, so the 3rd band is the multiplier. If you have 5 bands, so the 4th band is the multiplier. If you have 6 bands, the 5th band is the multiplier. So here in a 6-band it's like quite different. Like we also have the temperature coefficient. Still the 4th band would be the multiplier, but the 6th band would be the temperature coefficient. My apologies for that. Here you have yellow, you have purple, or sorry, my bad. Is it like violet? Yeah, it's violet. And then you have red. So that is 10 power 2. That is the multiplier like we're talking about. So it's like, say, 4, 7 times 10 power 2, or like just add 2 zeros to it. So 47, 2 zeros, 47,000, or like 4.7K. So that is the resistance of this resistor. And then we have a silver band. Silver band means like 10% tolerance, which means it could be 10% less or 10% more. So it's not going to be, when you say 4.7K, it's not going to be exactly 4.7K. It's going to change a bit. Like by how much does it change is indicated by this tolerance. So tolerance, it's measured in percentages. So it's the measure of resistors variation from a specific from the specified resistance value expressed as a percentage of its nominal value, right? And we also have something called temperature coefficient, and this will be again, like, you will not see much of these resistors because temperature coefficient is not that big of a deal unless you're like designing some really sensitive circuits, say for most of the prototypes we'll be dealing with. So 10 or like 5% resistors will be more than enough actually. So and in that temperature coefficient doesn't really matter. When resistance is really critical, that's when like we are going to also use the temperature coefficient. But again, it's good to know what is the temperature coefficient. So temperature coefficient is measured in like ppm. But apart from that, like, you will also have like ppm ohms per ohm. So that's the actual unit, but like we are dividing ohms by ohm, so those cancel out, and then like what you have left over is the ppm. It's parts per million, like that's we often use in chemistry. It's exactly the same, but again, parts per million ohms per ohm. So that's the thing. So let's calculate so that like it becomes easier for us. So here is a 6-band resistor. So I have brown, black, and then we have a red, and then we have a silver, and we also have a temperature coefficient that is orange. That's 15 ppm actually. So here, what does it mean? Okay, so maybe I just like flipped it around. So this has to be at the top. So let's go here. So that's 1 is for brown, black, 0, 0, and then we have red. So red, you will have to add 2 zeros, or you just have to multiply that by 100. So 10 power 2, that's 10 times 10 is 100. So you just have to add 2 zeros. And then you have the silver band, so which is 10% and 15 ppm. So what are these things? So you will have to explain these things as well. What does it mean? So for example here, so this is a 100 times 100. So this is 10K or 10,000. So that's 10,000 ohms or 10K resistor. Okay. So 10% of 10K is 1K. So the actual resistance, if you measure it with a multimeter, like it could read somewhere between 9 kilo ohms to 11 kilo ohms. So that is the range by which it can vary. Likewise, we have a 15 ppm, so which means, so 15 divided by a million, and that is 0.0000015 ohms per ohm. So you will have to multiply that by 10K or whatever resistance value it is per ohm. So usually these measurements are done at like 25 degrees Celsius. So let's say your resistors are going to operate in like say minus 40, or if it is going to operate at like say plus 50 or something like that. So at that point of time, if it is really critical, you will have to do this calculation, make sure how much resistance is going to vary, and then based on that, like, you have to modify your calculations. So that is the importance of this. But like if you see for a simple circuit, if you multiply this by 40, like how much is it going to be? So we are talking about the changes in the fifth decimal place. So that is not going to affect it that much. Or like, okay, we are going to multiply that. But again, like that is per ohm. Again, if you multiply, it's going to be like a big number, but still like that is not going to be huge. So you can disregard like for this for your calculations, but like again, this is something you'll have to take into consideration for while designing a very delicate sensitive circuit. So this is another example. So we have red, red, black, orange, and then we have a gold, and we have a brown. So again, you know what happens to brown in the temperature coefficient. So that is that, and red is 2, 2, black is 0, and then we have orange. Orange. Let's go back. What is orange? Orange is 3. So you add 3 zeros to it. So that is 220K. So 5% of 220K, because it has this gold band, it is 5%. 5% of 220K is 11K. So plus or minus 11. So it's going to be somewhere between 209 kilo ohms to 231 kilo ohms. So that is the range of resistance you can expect from this particular resistor. Okay, so let's start with some assignment problem. So here again, there are some resistors we might not even have the tolerance band, like for which like we generally assume that the resistance of those resistors are like 20% tolerance. So again, but here again, like we didn't give it on purpose, so you just have to calculate the resistor values. And so what is orange, white, and brown? So when you have these 3 color bands, what is the resistance? Likewise, you have all the colors, so you will have to calculate the resistance of these circuits. Oh, sorry, of these resistors, my bad. And so here, again, when you see a resistor, you will have to just start with the tolerance band and then go from the opposite side of it. So here, this is the gold band, so this indicates the tolerance. So here we go like this. I believe this is orange, orange, white, orange. So that is that. And again here, this is the gold band, and here this is the gold band, gold band, gold band, gold band. So okay, what is this? Yellow, violet, black, and that is a gold band. Okay, and here we have brown, I believe that's brown, brown, green, red, and we have brown, black, brown, and we have red, 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 and we have yellow, violet, and red. So these are the colors, and then you can find the resistance of that along with the tolerance. So we have the tolerance, so everything is gold, so gold is 5%, so the resistance is going to vary. So make sure you mention what is going to be the range of resistance here actually. Okay, so that is that. So let's go to the next slide, and you have another problem. So here we are going to use the formula. So for resistance in series, you can add them up together, and if it is parallel, you will have to find the sum of its reciprocal, and then like you take the reciprocal of that to get the equivalent actually. So here these 3 resistors are connected in series, so you add them up, and these, as soon as you add them up, you have 2 resistors in parallel. Then you can calculate the equivalent resistance of those 2 parallel resistors, and then you will have 1 single resistor, which is the equivalent of those parallel resistors. And now you have 2 resistors in series again. You will add them up, and then you will have another parallel one, so you will find an equivalent resistance there. So you will have, at last, you will have 3 resistors in series, like 4 ohm resistor, and a equivalent resistor of all these resistors, which will be here, and then you will have another 3 ohm resistor. You add them up, so you can just you will just have like 1 resistor, which is the equivalent of all these resistors. So you can do that. So again, maybe just to verify whether your answers are right, you can use Tinkercad, which we'll be learning towards the end of this module. But again, I would highly recommend you to use the formulas to calculate these and then check in Tinkercad. Okay. And that's the assignment questions. So we will be using something called a light dependent resistor. And the light dependent resistors are also called photoresistors. So these resistors are like sensitive to light. So as soon as it sees some light, the resistance of these material will decrease. And as soon as the resistor decreases, we can, if we have a circuit like that can measure current or voltage across those resistors, like say with that information, we can like turn on or turn off light, and we can do some cool projects with that. So those are like LDRs. So LDRs are like say made of semiconductor devices. So the way it works is like when the photons fall, so we know the light has particles called photons. So you know we can also look at as a wave as well. But like again, when these photons and come and strike these material, actually what happens is the electrons in these devices like move from the conduction band, not from the valence band to conduction band, it's the other way around, apologies, move from the conduction band to the valence band, and as the result of this you have like more free electrons. These free electrons will kind of aid in the conduction process. So that conductivity will increase, the resistance will decrease, and that's what happens. And if we can somehow read this as a current or like a voltage, this change in resistance, then like we can make use of this in our circuits to kind of understand light, or like say make our circuit respond to light. So again here, so when the electrons, or like when the photons fall on the device, so the electron actually move from the conduction band to the valence band, not the valence band to the conduction band. So that is something we'll have to change. So that is the photoresistor or light dependent resistor. So this should wind up the resistor submodule. So in the next module we'll start with semiconductor devices.